Pluto, once considered a legitimate planet in our solar system, remains a captivating and perplexing dwarf planet, situated far from Earth despite its former classification. Recent bold assertions by esteemed astrophysicists Neil deGrasse Tyson and Michio Kaku have stirred new interest in Pluto. They have suggested that Pluto's frozen world could be on a trajectory toward a catastrophic collision with Neptune, prompting a flurry of questions about the plausibility and consequences of such an event. Could this scenario be an exaggerated theory, or is there a legitimate cause for concern? Let's explore the potential ramifications of a Pluto-Neptune collision. Initially classified as a planet, Pluto was reclassified as a dwarf planet due to its irregular orbit, and this decision has kept it a subject of ongoing debate in astronomical circles. The latest studies by leading scientists suggest that Pluto's orbital path dangerously intersects with Neptune's, raising alarm about the possibility of a deadly impact. Given their proximity in their respective orbits, can a collision between Pluto and Neptune actually happen, and if so, what would the implications be? Pluto's journey around the Sun is unlike that of any other planet in our solar system. Its orbit spans an intricate 248 years, which means that since its discovery in 1930, Pluto has yet to complete even one full orbit. But the unusual nature of Pluto's orbit doesn't stop there. It follows an elliptical path that deviates significantly from the near-circular orbits of most other planets. To further complicate matters, Pluto's orbit is tilted 17 degrees to the ecliptic plane, making its trajectory much steeper compared to other planetary paths. An especially intriguing feature of Pluto's orbit is its intersection with Neptune's for about 20 years. During each of Pluto's lengthy orbits, it comes closer to the Sun than Neptune, a strange anomaly that contradicts the usual positions of these two planets in our solar system. This raises the important question, why haven't Pluto and Neptune collided yet? The answer lies in the powerful gravitational forces from other bodies in the solar system. After Pluto was discovered, astronomers quickly recognized the oddity of its orbit. Unlike the nearly flat orbits of the other planets, Pluto's steep angle and elliptical trajectory were starkly different. The complexity of its path became even more apparent as scientists realized Pluto's orbit crosses Neptune's. Despite these unconventional characteristics, Pluto's orbit has remained surprisingly stable thanks to the gravitational effects from other celestial bodies. The three-body problem in celestial mechanics seeks to explain the interactions and movements of three bodies such as Pluto, Neptune, and the Sun. Pluto's path through space can be erratic, as even slight changes in its initial conditions can result in drastic alterations in its trajectory over long periods. However, simulations have demonstrated that Pluto's orbit has remained steady over extended time scales, indicating that its path is not as chaotic as it may initially seem. The significant gravitational pull from massive bodies like Jupiter plays a crucial role in stabilizing Pluto's orbit for billions of years. These forces are essential in maintaining the overall order of our solar system and preventing any potential chaos, while Pluto's orbit demonstrates an intriguing balance of stability and chaos. It's important to recognize the inherent challenges in predicting the movement of celestial bodies, especially those with irregular orbits. Although numerical simulations can provide valuable insights, they also emphasize the unpredictability of space events, making long-term predictions uncertain. The concern raised by astrophysicists like Tyson and Kaku about a potential collision between Pluto and Neptune may seem far-fetched, but their warnings have caught the public's attention. If such a collision were to occur, the consequences could be disastrous for our solar system. The impact would release a massive amount of energy, likely leading to Pluto's destruction due to its small size and icy composition. The resulting debris could pose a significant risk to nearby planets and their moons, including Earth. The effects of a Pluto-Neptune collision would not be limited to Pluto alone. For Neptune, the collision could dramatically alter its atmosphere and orbit depending on the nature of the event. Michio Kaku, an acclaimed theoretical physicist, offers a unique perspective on this topic. His extensive research into string theory and celestial mechanics suggests that understanding Pluto's orbit could yield valuable insights into the physics governing space exploration. By examining the gravitational interactions shaping Pluto's orbit, we can gain essential knowledge for future space missions. This knowledge could help scientists better prepare for potential space threats and aid in the exploration of distant regions of the solar system, as well as beyond. The principles derived from Pluto's orbit also have broader implications for the study of other dwarf planets and transneon objects. Pluto's complex orbit challenges our understanding of planetary motion, reminding us that space is far more dynamic and unpredictable than we often perceive. The connection between celestial mechanics and string theory highlights the importance of understanding how planets and other celestial bodies interact. If Pluto and Neptune were to collide, it could become a landmark event in cosmology, offering a rare opportunity to explore string theory's predictions under extreme conditions. This collision would release vast amounts of energy and could potentially offer a glimpse into the behavior of elementary particles and forces at high energy levels, a major focus of string theory. Although the direct impact on Earth would likely be minimal due to our distance from the outer solar system, the broader scientific implication would be profound. Such a collision would provide new opportunities to explore the universe's fundamental nature, particularly in areas relating to string theory and theoretical physics. The unusual orbit of Pluto continues to capture the imagination of both astronomers and space enthusiasts, and the ongoing debate over its status as a dwarf planet has reinvigorated interest in its role within our solar system. The concerns raised by Tyson and Kaku underscore the complex forces that govern the movements of celestial bodies, emphasizing the importance of understanding gravitational influences and orbital mechanics. These forces are vital for comprehending the dynamics of our solar system and the ongoing debate surrounding Pluto's status as a planet. Pluto's elliptical orbit and steep inclination defy conventional models of planetary motion, unlike the nearly circular paths followed by its neighboring planets. Pluto's orbit crosses Neptune's at certain points during its long journey around the Sun. The gravitational forces exerted by Neptune and other planets have played a significant role in stabilizing Pluto's orbit, ensuring it remains relatively constant over centuries. Despite this, predicting the future behavior of celestial bodies remains a complicated and unpredictable task. The possibility of a Pluto-Neptune collision serves as a reminder of the inherent uncertainties in planetary dynamics. Although such an event seems highly unlikely in the near future, the gravitational interactions between Pluto and Neptune illustrate the delicate balance that exists within our solar system. By studying Pluto and its moons, scientists gained invaluable insights into the diversity of celestial bodies and the conditions found in the outermost parts of the solar system. These discoveries have profound applications for future missions to explore other distant dwarf planets and transneon objects, providing scientists with more information about planetary formation and evolution. Pluto's reclassification as a dwarf planet has sparked important discussions about how we define celestial bodies within our solar system, reflecting broader questions about scientific classification and the evolving nature of our understanding of astronomy. Studying Pluto's orbit offers vital insights into celestial mechanics and planetary dynamics, especially as we venture further into the outer reaches of the solar system. By exploring Pluto's interactions with Neptune and other celestial objects, we continue to expand our knowledge about the formation and development of planetary systems. Pluto's discovery and ongoing study have significantly contributed to our understanding of planetary motion and the formation of the Kuiper Belt, a region beyond Neptune filled with small icy bodies. Understanding Pluto's orbit provides valuable clues about the gravitational interactions that may have shaped the early solar system, offering essential information for future space missions focused on exploring potentially habitable worlds outside of our solar system. Although the likelihood of a Pluto-Neptune collision remains extremely low, the study of these celestial objects serves as a reminder of the ever-ranging nature of the universe. As we continue to explore the far reaches of our solar system and beyond, the study of planetary orbits and celestial mechanics will remain central to our exploration efforts. Pluto's unique orbit offers valuable lessons about the complexities of planetary motion and the forces that shape celestial bodies over time. The continued exploration of Pluto's orbit and its interactions with Neptune serves as a reminder of the unpredictability of the universe. With each new discovery and theoretical model, we expand our understanding of the cosmos and gain insights into the mysteries of distant worlds. The study of Pluto's orbit not only provides answers about this distant world, but also helps us predict future trends in celestial behavior, contributing to a better understanding of the forces that govern our solar system and beyond. In conclusion, the possibility of a Pluto-Neptune collision, though highly unlikely, underscores the dynamic nature of the universe. The study of Pluto's orbit, its interactions with Neptune, and the gravitational forces at play offer valuable insights into celestial mechanics. As we continue to explore these distant bodies, we refine our models of planetary systems and enhance our ability to predict future cosmic events. The potential for discoveries in this field is limitless, and as technology advances, so too will our ability to study and comprehend the vast ever-changing cosmos. The exploration of Pluto's orbit and its role in the solar system will continue to shape our understanding of the universe for years to come. Pluto's orbital behavior with its unique interactions with Neptune has long been a subject of fascination and intrigue within the scientific community. Despite its designation as a dwarf planet, Pluto continues to challenge our understanding of planetary dynamics. The fact that Pluto's orbit intersects Neptune's at various points without resulting in a collision highlights the complex nature of gravitational mechanics in our solar system. One of the most fascinating aspects of Pluto's orbit is its resonance with Neptune. This resonance, known as a 3:2 orbital resonance, means that for every 3 orbits Pluto completes around the Sun, Neptune completes 2. This carefully synchronized relationship ensures that the two bodies never come too close to one another despite their crossing paths. In this resonance, Pluto and Neptune are essentially locked in a cosmic dance, where their orbits are set in such a way that they never collide. This unique gravitational relationship is an excellent example of the precision and balance that exists in celestial Mechanics: the forces exerted by Neptune's gravity on Pluto and vice versa work together to maintain a stable orbit for both. Without this resonance, Pluto's orbit could have been disrupted, potentially leading to a collision or other significant perturbations in its trajectory. Understanding this interaction is crucial for astronomers, as it provides insight into how celestial bodies can maintain stability, even when their paths seem chaotic at first glance. Moreover, the Kuiper Belt, a region beyond Neptune, is a treasure trove of icy bodies and dwarf planets. Pluto is the largest known object in this belt, and its orbit provides valuable information about the conditions that prevail in this distant part of the solar system. The Kuiper Belt objects, KBOs, and Transnunian objects, TNOs, are remnants from the early solar system, and their study allows us to peek into the conditions that existed during the formation of the solar system. Billions of years ago, space agencies like NASA are now directing missions towards studying these far-off regions. NASA's New Horizons mission, which conducted a flyby of Pluto in 2015, provided us with unprecedented images and data about Pluto's surface and atmosphere. The findings of this mission revealed frozen nitrogen plains, towering ice mountains, and a complex weather system, suggesting that Pluto is a geologically active world. It also showed the diversity of the dwarf planet moons, providing clues about how moons form and evolve in the outer solar system. The New Horizons mission also illustrated the growing capabilities of modern space exploration. Such missions not only expand our knowledge of distant celestial objects like Pluto, but also paved the way for more ambitious explorations into the Kuiper Belt and beyond. The success of this mission has sparked renewed interest in exploring these far-flung regions and could inspire similar missions to other objects within the belt. Despite the apparent stability of Pluto's orbit, its eccentric and tilted trajectory also raises questions about the long-term dynamics of the solar system. The fact that Pluto's orbit is so different from the nearly circular orbits of the 8 major planets offers astronomers a fascinating puzzle. The inclined and elliptical nature of Pluto's orbit serves as a reminder that our solar system is not as orderly as it might seem at first glance. The chaotic behavior exhibited by Pluto's orbit could have profound implications for our understanding of planetary formation and evolution.